that we have to describe them basically as wave functions and their relative energies. And now what we want to try and figure out, or to be able to describe, is in multi-electron atoms, what's the arrangement? How are electrons placed in these multi-electron atoms? And what does that ultimately tell us about their behavior? So what we're going to talk about is how that works. And then we are going to, so first we're going to talk about how electrons are arranged in atoms. And then we are going to talk next about how that arrangement affects their physical and chemical properties. It also turns out that where an element is on the periodic table, also in which group an element is in, tells us what type of orbital those valence electrons are in, with the exception of hydrogen and helium. But for example, if atoms in group 1 and group 2 all have their valence electrons, their outermost electrons, in s orbitals, atoms from group 13 on to group 18, they all have their valence electrons in p orbitals. These guys here in the transition metals, they all have their valence electrons in ds, and these guys all have their valence electrons in f. The way that we look at things, so mostly we're going to be focusing on this version of what we call an orbital diagram. All right, so this is basically, we have energy going up and we have the different orbitals. And this is for a hydrogen atom, so we don't really care about that most of the time because one electron's not that interesting. We're going to be looking at this. Now, the way we think about most of this stuff, and there's this equation comes up all the time in this class. The good thing, the best thing about this equation in this class is that you almost never have to use it, and you actually never really have to use it. But it is the guiding principle. So we don't have to use it necessarily mathematically, but in terms of the principle of it, we do need to use it. And so basically, Coulomb's law tells us that the force of attraction between charged particles is equal to some constant multiplied by the product of the charges, and it's the absolute value of the product of the charges, divided by the square of the distance between them. Really, for this class, the most important thing is not the actual equation, but rather the proportionality of this equation. So the energy of attraction or repulsion between charged particles is the product of the charges divided by the square of the distance between them. So the closer an electron is to the nucleus, the stronger the attraction will be. And when electrons are close to the nucleus, they have a very strong attraction to that nucleus. Systems tend naturally to want to have the lowest possible potential energy, or opposite charges attract each other as much as possible. We are always going to have the lowest energy orbitals filled first. This clearly, the 1s orbital, which is in kind of this purple that skyrockets here, the total radial probability here of the 1s orbital, very close to the nucleus. So this has the strongest attraction to the nucleus, and so the s orbitals, and the 1s orbital is the lowest energy orbital. Now, after that, the next set are the orbitals that have n equals 2, and we have 2s and 2p. Now, interestingly enough, on average, the 2s orbital is actually further away from the nucleus than the 2p. However, if you remember the shape of s orbitals, when we cut them open, the bigger ones, there's this region of probability very close to the nucleus. And so this bit here actually ends up counting for quite a bit in the calculation of the attraction to the nucleus. And it's not as straightforward as the equation that I showed you, but more or less. The s orbitals penetrate close to the nucleus. There's a region of probability closer to the nucleus. And because the force is proportional to 1 on r squared, because the r portion is squared, this bit ends up counting for quite a lot. So even though on average, in a given energy level, s orbitals are slightly larger than p or d orbitals, because they have regions that penetrate very close to the nucleus, they are lower in energy, which means s orbitals get filled first, right? And then d orbitals last. So the method that we use, and it works quite well for the first bunch of atoms, right? So it works really well up until, say, I guess krypton, really. After that, it's a bit of a mess. But when we're dealing with relatively small atoms, it works reasonably well. And the method is known as Aufbau, which is German for building or building up. Or the idea is if we want to know the arrangement of atoms, of electrons in an atom, we can set ourselves up with a diagram like this, and this should say like this, and it should say energy. We add electrons one at a time until an orbital is full, and then we keep moving. If I had lithium, right? Lithium is the third element on the periodic table. It has an atomic number 3. So if it's just lithium 0, it has 3 electrons. The way I add electrons to this to figure out the configuration is, well, I add my electrons, and remember we represent electrons as a half-head arrow, and we use the direction that the arrow points to represent the spin quantum number. So that's 1 electron. Now remember, each of these lines, sometimes you see them represented as boxes. Each of these lines represents an orbital, and each of them can hold 2 electrons. So that's 1 electron, 2 electrons, 3 electrons. So the electron configuration for lithium is going to be 1s2, 2s1. Now, it's not 1s squared. The 1 is what orbital, right? 1s, 2s, whatever. This is how many electrons are in that orbital. So this is the electron configuration for lithium. Really, you just continue the process that way. Now, if I were to look at something that has more electrons in it, it may get a little more complicated. Like, for example, let's take something like nitrogen. So nitrogen is 5th, has 5 electrons. Really, the way I do this is 1, 2, 3, 4, 5. Now I have to start thinking about how I'm going to handle this. If we backtrack a little bit, and so with my 7 electrons, it should be relatively clear why the electrons pair before I fill the next. Remember, when I pair electrons, there's a repulsion. But even for something as simple as dealing with 2 electrons, I have 2 possibilities. Either I can arrange my 2 electrons like this, or I can arrange my 2 electrons like that. So this would be, for example, for helium. So I have a possibility that either my electrons are arranged like this or like this. Now, this version here is lower and has a lower energy, a more stable system because the 2 electrons are closer to the nucleus. And even though there's a bit of repulsion between those 2 electrons, it's not nearly as much as any instability that would come from having the 2 electrons like that. So this is the lower energy configuration. So this is the version that this is why we always fill up these lower energy orbitals before moving on. Now, the thing is, when we get, eventually we'll get back here, when we get to the nitrogen with its 7 electrons, so we have 1, 2, 3, 4, 5. Now I have to decide, where does the next electron go? Basically, I have 2 possibilities. Up until now, what have we done? We say, all right, I have 1 electron in an orbital. I put the next electron in an orbital, right? So that means I could put that one there. But remember that this axis is energy. So what does that tell us about the energy of each of the different p orbitals? The energies of all the different orbitals are the same, which means I have a different possibility. Yeah, that's right. So we put the arrow separate. So here, if you look, this version here, this is the lower energy arrangement, like this. So the electron configuration for nitrogen would be 1s2, 2s2, 2p2. We don't usually differentiate between px, py, and pz, right? We just group them all together. And I'm still missing, actually, I jumped ahead of myself, didn't I? I'm missing another. This is only 6, and then 7. There we go, 2p3. There we go. So this would be the lowest energy arrangement for nitrogen. The rule that we follow here is called Hund's rule. When we have degenerate orbitals, we put one electron in each of the degenerate orbitals before we start pairing up. This method, just following the rules as we've done it this way, works really well up until about argon. But things get really messy when we start getting higher up on the periodic table, more towards, say, the transition metals. What happens is as we get further and further away from the nucleus, the effect of the nucleus becomes a little less strong, and the energies of the orbitals actually start to kind of overlap with each other. As we get further and further away from the nucleus, what happens, you'll notice that the 3d and 4s orbitals have almost exactly the same energy. And so once we get past argon on the periodic table, things get a little wonky. So in our periodic table here, you can really tell about the valence electrons, the outer electrons on an atom or an element based on its position in the periodic table. And you'll see that mostly we only care about valence electrons in chemistry because those are the electrons that are going to end up doing stuff. So we saw lithium, its electron configuration was 1s2, 2s1. Well, guess what? It's in the second row of the periodic table, and it's in the first row here, the first group, 2, and this is the S block, 2s1. Nitrogen was 2s2, 2p3, so 2s1, 2s2, 2p1, 2p2, 2p3. So you can use the periodic table almost without, actually without fail up until argon. After that, it gets a little messy. What we find is that it does hold reasonably true. So for example, when we get to argon, the electron configuration of argon have a full 3p orbital. When we get to argon on the periodic table, its 3p orbital is full, and the natural tendency is to think that the next available electron is the next available orbital would be the 3d orbital. But it turns out that actually the 4s orbitals fill before the 3d orbitals, and this is again because s orbitals penetrate closer to the nucleus, so they are lower in energy, even though they're slightly larger than the 3d. 4s orbitals are just a little bit lower in energy than the 3d, so the 4s orbitals actually fill first, and this corresponds really well to what we observe and what early chemists and Mendeleev observed when they were trying to classify things, which is that, say, for example, lithium, sodium, potassium, they all have similar chemical properties. They all do the same types of reactions. They all have very similar physical properties and so on. And the same thing goes here with beryllium, magnesium, calcium, and strontium and so on. They all are very similar, so they're grouped together. And one of the key messages of this class for matter is that structure determines function. And in this case, electronic structure determines function. So how are the electrons arranged? That determines the function. And these guys here have their valence electrons in 1s orbitals. And it's logical and it makes sense that potassium also would have its valence electrons in s orbitals, and so would calcium, because they follow this trend. And it turns out that it works out, in fact, that way. So what happens is that when we get here, once the 3p orbital is filled, the next available orbital that is filled is in fact the 4s orbital. So if we look at, say, calcium and potassium, we put the next available electron into 4s. All right. Now you notice that over here, I start using a certain type of shorthand. Right. This is called the noble gas configuration, and you're always allowed to use it unless I specifically say not to, but I would encourage you to. All right. And basically, and you're only allowed, the convention is you only use a noble gas. Basically, the idea here is this arrangement here, 1s2, 2s2, 2p6, 3s2, 3p6. This is the electron configuration of argon. So when I'm writing the electron configuration for an element that comes after argon, I can just do this. I put argon in square brackets and then write whatever comes next. These electrons here are what we would call core electrons. This is a valence electron. And again, this highlights the fact that as chemists in general, we really only care about valence electrons. For the transition metals, once we get past potassium, calcium, then we get to scandium. Now we start adding electrons to the 3d orbital. So 4s and then 3d. All right, so you notice that for here, if I want to know about the valence electrons for something in this group here, and this group here. So what we would, these are often referred to as the main group elements. The rho is equal to n for the valence electrons. Lithium we saw is in rho 2, and its valence electrons are in n equals 2. The rho minus 1 is equal to n for the valence electron. These guys, scandium, titanium, vanadium, so on, their valence electrons are in 3d, even though they're in the fourth row. When we get to these guys here, right, the lanthanides and actinides, all right, the rho, it's not really the rho because they're sort of popped out. It's the rho minus 2 equals the n for the valence electrons. So for example, cerium is in rho 6. So its valence electrons are going to be in 4f. Thallium here is going to be in row 7, and so its valence are going to be in 5f. When we get to the transition metals, the 4s is filled, and we start adding electrons one at a time. And because the d orbitals are degenerate, they're all the same energy, we add them across one at a time. So scandium would be 3d1, 4s2, titanium, 3d2, 4s1, vanadium, no. But then all of a sudden we get to chromium and this happens. So that sucks. What happened? The rules kind of start to fall apart. And as I said, as we get further and further away from the nucleus, these Aufbau rules, which are, remember, these aren't nature's rules. This is a method that we use to try and figure out what's going on. It turns out that this arrangement of, so chromium, there are two exceptions basically to the rules as we go through the transition metals. Chromium and copper, you're expected to know them. So chromium is over here on the periodic table. So if we have chromium, we have argon, and then how many other electrons do we have? We have 1, 2, 3. We have 6 extra electrons that we have to play with for chromium. So it's argon plus 6 electrons. And so I have 4s, and then 1, 2, 3, 4, 5, 3d. All right. Now, if we follow the regular Aufbau rules, we would expect this 1, 3, 4, which would be 4s2, 3d4. Now, you're going to see when it comes to the electron configuration of transition metals, you're going to see things written different ways. For example, I could write the S first or the D first. The new convention is put the D's first, and we'll get to that in a second. So this is one possibility. But it turns out that based on a bunch of experimental evidence, that's not the case. The actual arrangement is, which would give us argon 3d5 4s1. The reasons for this are really complicated. If you do the calculations, it turns out that this arrangement is actually lower in energy than this arrangement. There are a bunch of empirical observations that support this. So when we say something has empirical evidence, empirical means from experiment or observation. And one of them is that chromium is one of the few transition metals that makes a +1 ion. Magnetic behavior of elements is dictated by their electron configuration. And what that means is elements that have unpaired electrons are attracted to external magnetic fields, and elements that don't have unpaired electrons are repelled by external magnetic fields. And the magnitude of that attraction is related to how many unpaired electrons there are. So chromium is one of the exceptions, and copper is the other one. Chromium here is 3d5 4s1. Then we go back sort of the regular pattern until we get to copper, and copper is 3d10 4s1. So these two exceptions I expect you to know. All right, the other ones follow the rules. By the time we get past krypton and then into the next row of the periodic table, there are so many exceptions that we basically don't bother using it, right? Now there's like this is an exception, this is an exception, exception. There's so many exceptions that there's not really a rule anymore, is what it is. All right. So the Aufbau principle works reasonably well up until krypton, and then after that, not so great. All right, especially for transition metals and for the F block, the actinides. What I want you to try and get used to doing is to look at the periodic table and see if you can figure out, based on where the element is on the periodic table, what its valence electron configuration is going to be. Because one of the things that I want you to remember is that you're always, when I'm asking you to write out electron configurations, you're always going to be allowed to write out condensed electron configurations. And it's important to realize that so that we highlight the valence electrons, because those are the ones that we care about the most. Those are the ones that do stuff. Those are the ones that get given or taken in ionization. Those are the ones that get shared in covalent bonds. Those are the ones that dictate things like how big the atom is and so on. So what we want to do is pay attention to those. And as I've mentioned, one of the things we can do is we can look at the periodic table and figure out what the electron configuration is for the valence electrons based on where the atom is on the periodic table. I'm just going, if you remember, the elements that we have here, right? All of these ones so the first two rows, these are the S block. So these guys all have their valence electrons in 1s. Here, these ones, or not in 1s, but these guys all finish in S1, and these ones finish in S2. The transition metals, all the way here, this is the D block. So their valence electrons are all in D. And if you want to know which energy level in D, what the value of N is, it's always going to be the rho minus 1 for these guys. And then this block here, not including helium, right? These are the P block. And again, when we get back to the P block, it becomes much easier because in group 13, these are all P1, P2, P3, P4, P5, and P6. Now, in the D block, it's pretty straightforward. So except for chromium and copper. And so you need to remember those two exceptions. These guys down here have their valence electrons in F, and we don't need to really know anything. The rules, they don't really apply. There's knowing the configurations is, or predicting the configurations rather, is really complicated. So strontium is here. This is SR. And so the electron configuration of strontium is krypton 5s2. And now if we look at the general rule is, except for the transition metals, the last electron that we add is the first electron that comes out when we're making cations. The highest energy electrons, for the most part, are the ones that are removed first when we ionize. So in our case, the highest energy electrons are these ones in the 5s. So that's for strontium 0. So strontium 2 plus will have lost 2 electrons. So its electron configuration will just be krypton, which we can represent as argon 3d10 4s2 4p6, right? And so the valence electrons are these ones. What happens when we add or remove electrons? We're going to start with removing electrons since we're already at it, and it's a little trickier. Adding electrons is pretty straightforward. So in general, the general rule for removing electrons, for making cations, is that the highest energy electron, the last electron in, is the first electron out. And that's it. All right. And then typically, once the valence electrons are removed, then it becomes too difficult to remove anymore. And we're going to see more about that, I guess, starting on Friday. So if we look, for example, all right, let's do aluminum. So aluminum with no charge, the element aluminum is here. So its valence electron is 3s1, 3s2, 3p1. I'm going to write the whole thing. So its valence electrons are neon 3s2, 3p1. I could also write this out fully. 1s2, 2s2, 2p6, 3s2, 3p1. All of the electrons that are hiding in this shorthand where I write neon, that's these ones here, and these are referred to as the core electrons. They don't do anything. They do have an influence a little bit, but really they don't do much. As a general rule, as chemists, we don't care about them. We ignore them. I mean, they're there, but we don't pay too much attention to them. What we care about are the electrons with the highest value of N. So these are the valence electrons, and these are the ones that do stuff. Now, when we're looking at ions, the way we look at this is we add or remove one electron at a time and see where that gets. Aluminum has 3 valence electrons, and the common ion of aluminum is Al3+, right? And guess what? It's these 3 electrons that come out. So aluminum 3 plus has the electron configuration 1s2, 2s2, 2p6. So basically that's it. It's just the highest energy electrons are removed. That's all there is to it, honestly, except when we get to transition metals. So when it comes to transition metals, the rules are a little bit different. In transition metals, the valence electron, s electrons, are removed first. So I'll give you some examples. If we look at the case of one of my titanium. So titanium is here, it's number 22. So that's argon, 4s1, 4s2, 3d1, 3d2. Titanium 0 is argon, 3d2, 4s2, like that. All right. Now, titanium makes two different ions, right? One of the things, if you remember back from NYB and naming, is that transition metals often make different ions, and it's because of this their electron configurations, in fact, that these different ions are possible. So titanium 2 plus, what happens is, even though when we do our Aufbau, the last electrons that we put in are the D ones, right? But in fact, what happens is these are the ones that come out. So titanium 2 plus is argon, 3d2, 4s. Now, here's the thing. You don't have to write the 4s0. There's no electrons in it, so we don't write it. We would just write argon 3d2, right? That's how you would write it. That's it. The other ion that titanium makes is titanium 4 plus, which is just argon. So the general rule is when we are ionizing, very often the different ions we see are that the valence orbital or one of the valence orbitals is completely emptied, or maybe it's emptied halfway or things like that. So for example, in titanium, there's no titanium +1 ions observed. I mean, I imagine under certain experimental conditions you could generate one, but they're not a commonly occurring ion, say, on Earth, right? What do we see? We see titanium 2 plus, which happens when the 4s electrons all leave, and titanium 4 plus when all of those electrons are gone. Oh, geez, that's not actually an intended pun. Calculations to support this, all right? And one of the most important bits of evidence comes from resulting electron configurations and their behaviors. So a classic example of this is copper. The electron configuration of copper, remember, is argon 3d10 4s1. Copper forms two ions. The first one is copper +1, which is argon. We expect it to be argon 3d10 4s0. I'm just going to write the 4s0. This is where the magnetic behavior of elements is really important. Basically, when it comes to pairing of electrons, there's two possibilities. Either there are no unpaired electrons, or an atom or an ion has unpaired electrons. Now, when something has no unpaired electrons, the word that we use to describe it is that it is diamagnetic. And things that are diamagnetic, they are repelled by external magnetic fields. What does that mean? It means if something has no unpaired electrons in it, no matter how strong the magnet is, for example, it will never be attracted to a magnet, even if it's a metal, right? It'll never be attracted to a magnet. It will always be repelled. I mean, often the effect of diamagnetism is pretty weak, so be weakly repelled. When something has unpaired electrons, the term for it is paramagnetic, right? And it is attracted. So we can tell based on how something responds to a magnetic field whether or not it has unpaired electrons. And so copper metal has one unpaired electron, and so we would expect it to be weakly attracted to external magnetic fields. It turns out that the degree of attraction is related to the number of unpaired electrons. But copper plus 1, in contrast, should have no unpaired electrons because the 3D orbital should be full, right? If I write out its electron configuration, so it's copper plus 1, it's argon, right? And so the D, it's not going to work very well. No, that's annoying. Has lines. 1, 2, 3, 4, 5. And then, so this is 3D, and this is 4s. So if I put in my electrons, right, so it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So copper plus 1 has no unpaired electrons. It is diamagnetic. Okay. Now, so if I take a compound that has copper 1 in it, it should be repelled by external magnetic fields, and this is actually something that we do observe experimentally. Copper 2 plus then, right, would be starting from copper 1, should be, we take away again one more electron. One, two, three, four, 5. Now, here's the thing. It doesn't actually matter which of the electrons I remove from 3D. I don't think it's actually even possible to tell. However, by convention, I'm going to just do that. And so that one's missing, right? So copper 2 plus then is argon 3D9. And now again, it has an unpaired electron, and I would expect copper 2 compounds to be attracted to magnetic fields, which they are. Right? So, and the same is true for zinc, or actually all of them. So the key difference between the main group elements and the transition metals is that for the main group elements, it's always the highest energy electron that comes out first. For transition metals, it's always the s electron. In our case, it's really going to be limited to the 4s. Those electrons come out first, then the d electrons start coming out. Now, anions are more straightforward. So the first thing to realize is that metals in general don't form anions. They can be induced to form anions. Hydrogen does form an anion, hydride ion, which is -1. But typically the nonmetals, and especially the nonmetals in here in green, right, what we might call the reactive nonmetals. The metalloids, not so much. They behave much more like metals than nonmetals, but these guys here in the corner, these are traditionally the elements, and typically, not traditionally, but typically the elements that form anions. And the charge on those anions can be deduced from the position on the periodic table, but it's not actually based on the position on the periodic table, right? That's not why something happens. The reason something has a charge or forms an ion that it does is because of its orbitals, right? So if we take something like fluoride ion, all right? So fluorine is over here. It's element number 9, 1s, 2s, 2p, right? So fluorine has 9 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So that means there's basically, so 1s2, 2s2, 2p, 5. So there's one empty spot in the 2p orbital. And so F minus 1s, 2s, and 2p. So remember, if something has a negative charge, it means it's gained electrons. And if it has only a -1, that means it's gained 1 electron. So I should have 1 electron. So 1s, 2, 8, 9, 10, right? So it's 1s2, 2s2, 2p6. Now, the thing is that fluorine, for example, can't accept any more electrons because the energy gap between n equals 2 and the next available orbital would be the 3s orbital. And the amount of energy required to have an electron in 3s and hold it there, right, is too big for the nucleus. So remember that the reason electrons stay with an atom is because of their attraction to the nucleus. But at some point, it just becomes too difficult. There's too much. It's too hard for the nucleus to hold on to more electrons until the nucleus actually gets bigger. So basically, the idea with anions is you add electrons until the valence orbital is full, and then you stop. One of the things I want you to be clear about is that when I ask you to explain something, so let's say on a test or a quiz, I say, how come fluorine only forms a -1 ion? You cannot get it. It's not correct. I mean, you could write it, but it's not correct to say fluorine is halogen and it's and based on its position in the periodic table, it's one away from a noble gas, and that's why, right, it wants 1 electron to be like neon. That's not the right answer, right? The periodic table is a human construction. It's not the cause of anything. We use it to help us understand things, but it's not, the periodic table doesn't exist in nature. If you want to explain why fluorine only forms a -1 ion, right? Well, you say, look, there's 1 electron. There's 1 electron missing from its valence orbital, and so it has room for 1 more electron. Otherwise, the nucleus can't hold on to any more electrons, and we're going to talk more about that a little bit later in more detail, right? And so for anions, it's very easy. You just figure out how many missing empty spots there are in the valence orbital and add enough electrons to compensate. That's really it. Students typically get screwed up on the transition metals. It's easy to forget that it's always, for any of these transition metals, any electrons in the 4s, those are the ones that come out first. Questions about this? No? All right, just give me a second.